Coming down to the wire, this is the last chapter we're going to cover this semester, Electrochemistry, chapter 18 in your textbook. And I'll start by sharing. Let's see. Where is it? There it is. Okay. And let's get the slideshow going.
All right.
Come on. Slideshow. There we go. All right. So, electrochemistry. You might think it's self-explanatory. Electrochemistry having to do with chemistry in which electrons are exchanged. And that in its simplest form is the correct definition. But of course, as you may suspect or even fear, there's more to electrochemistry than just the name. We need to review some terms because we're going to be using some words that may be unfamiliar to you. Besides the fact that electrochemistry is the study of chemical changes that involve electrical energy changes as well. The first definition, actually this first one is a combination of these others. So I'm gonna go down here and work with these others first and just use a generic reaction. So whenever we have a reaction that involves these reactants and these products, what can happen, doesn't have to happen, but what can happen is that one of these reactants can either lose electrons or gain electrons. And let's just, for the argument's sake, let's say that this one loses an electron. We have a loss of an electron here. One thing about electrons is when one species loses an electron, somebody else has to pick up that electron. Otherwise, you have an electrostatic charge, and most, if not all, chemical reactions are balanced in electrical charges. Let's just say all are, because cases where you have unbalanced electrical charges in chemical reactions are so rare as to be non-existent. So if this one loses an electron, that one has to gain the electron. So we would transfer an electron over here like that. Okay? So we have special names for these. For the one that loses an electron, we call it, this process, oxidation. And for the one that gains the electron, we call it reduction. All right. And there's a little acronym that will help you remember these. It's called oil rig. Oxidation is loss. Reduction is gain. Okay, so if you get stuck, just remember that. Oil rig, and it'll put you back on course. All right, so when we say that this species is oxidized by losing an electron, whenever you have an oxidation of one species, the other one has to be reduced. That is, they always go in pairs. So this becomes the reducing agent. for that species. Right? This is the reducing agent for that one because it becomes oxidized. This one becomes reduced. So you might have already guessed this one is the oxidizing agent. Okay. All right. So those we've got those terminologies down, and the whole process taken together is called oxidation reduction. Okay, just oxidation reduction reaction. Or for short, we say redox. We say redox because it flows better off the tongue. Ox-red just, for some reason, just doesn't sound right. So we say redox. Okay, there's your acronym. Now that we understand the terminology, how do we use this information to investigate and ultimately balance chemical equations? Okay, my board's going to be difficult today. So expect some sort of collapse or accident. Yeah, I can't do with that. 1 second. I'm going to have to strip the board. It's got something on it that's retaining the marker. Be right back. Use a little polar, non-polar chemistry here. Oh, there we go. Get you 4 inches at the bottom. Yeah, that's better. Now the question is it going to do the same thing with my marker as it did before? Be sure it's dry. That's a little better. Okay, let's carry on. So now that we know what oxidation and reduction is and what it means in terms of each of the reactants, we're going to use that information to balance equations in which electrons have been transferred. Right? For an oxidation or reduction to occur, an electron has to be transferred. So this is the most efficient way to balance, and well, best is not the right term. It's all inclusive. The best way to balance a redox reaction is method of half reactions. Okay. The method of half reactions also sets us up for the use of those half reactions when we construct an electrochemical cell. Now, I'm going to have to define that electrochemical cell later, but we need to learn how to balance equations by this method before we can move to the next step. And another name for an electrochemical cell is a battery. So what do we do with a reaction that we know involves oxidation reduction? We split it into two reactions, one for the reduction half of the reaction and the other for the oxidation half of the reaction. Now this example that's given in the slide has already been balanced. So it's there just to illustrate that with this balanced equation, it can be represented by these two half reactions. Right? In this one, the reduction occurs for, and when you write a half reaction, you will have some species or more, could be more than one, like this one has more than one, but the electrons go on the reactant side because they're being added to this one to produce something over here. Right? So where did that electron go? Well, it went into this and formed a product. Okay, so this is your reduction, and the electrons always occur on the reactant side. For the oxidation side, you would have something like this, and the electrons occur on the product side. Okay, so that's convention, and it's logical. All right, so for this example, this reaction can be split into these two. Now, how did we know to put hydrogens here with this one rather than with the iron down here? Well, I'm going to show you that by the method of balancing the equation. Then it'll become clear as to why the hydrogens are retained in the reduction side and not in the oxidation side. All right. So how do we, oh, there's Heather.
Can
Where'd
you see
go?
me okay?
There you go. Yeah. Let's see. Let me change my view. There we go. So I've got everybody in a row or in a column.
Okay.
Heather. Steffi was here, but she keeps dropping out. I think she's got bad internet connection today.
Yeah, mine's pretty bad too.
We got sunspots maybe.
I don't know what's going on, but it's just been a nightmare.
Hi.
But good morning.
Good morning. I lost my internet yesterday for about a half an hour, which is unusual for Suddenlink. They're very reliable.
Yeah, usually. I have Frontier.
Oh, you have my sympathies.
Thank you.
I used to be with Frontier's predecessor, and when Frontier showed up, they actually got worse.
Yep.
With so you must have DSL, right?
Yeah, it's just not a good situation, but we do the best we can, right?
That's probably all you have in your area, isn't it?
Yeah.
Yeah.
Yeah, but my family has Frontier too, so like if I even went home, they have the same thing. So there's really
no advantage.
No win or yeah, no win-win. It's just you got to make do.
Yeah. Do you have good cell service?
No, it's usually Wi-Fi. So like when the power went out last week, it was very spotty, so I really couldn't use my phone either.
Oh, okay. Well, let's see. Let's carry on. And I'm just getting ready to introduce the method of half reactions. I've explained reduction, oxidation, and what they mean, and the acronym oil rig, which is on a previous slide, that will help you come back to center if you forget which one is which. Oxidation is loss, oil, and rig, reduction is gain. And that's referring to the electrons. So an oxidation is a loss of electrons, reduction is a gain of electrons. And they always occur together. You can't have one without the other. So this equation is an example of a balanced equation in which an oxidation and reduction has occurred. And we split it into two reactions, one describing the reduction side, and the electrons always occur for a reduction on the reactant side. And those that the same number of electrons, notice, have to occur on the oxidation, on the product side for oxidation. So that's why when you combine the equations, the electrons disappear. because they cancel each other out, mathematically speaking, but they're still there. Okay, so let's get to an example. These are the procedural steps for balancing an equation by the half reaction method for acidic solutions where you have an excess of protons. And I'm going to show you how to do basic solutions later, but we need to learn this one first. So the first thing you do is you write the separate equations for the oxidation and the reduction halves reactions. You just split it apart. You have to decide which one's being oxidized and which one's being reduced, and then split those into separate equations. I see Kessa. Okay. Kessa, here we go. All right. So once you've got them split, then you balance all the elements in each of the equations except for hydrogen and oxygen. Once that's done, then you go in and you balance the oxygens using water wherever necessary. This will become clearer once we do an example. And after you balance the oxygens with water, you balance those extra hydrogens that you just added with protons. And the final step is you balance the electrons. Okay? If necessary, before you can combine the equations, you have to be sure that you've got the same number of electrons in the oxidation equation as you do in the reduction equation. Because when you combine them, the electrons have to cancel. And then you can go back and do a check to be sure that all the elements and charges are balanced. Okay, so this is what it looks like in a schematic form. If you're prone to that, that's fine. Whatever suits you. Okay, here's an example. So we're going to take dichromate and react it with the sulfite ion and yield chromium 3+ and sulfate. Now, the first thing that is obvious to me is you've got all these charges in here, and the charges don't balance. Right here, you've got a +1 excess, and here you've got a -4. So when you put those together, what's obvious to me is that each one of these is placed into solution with a counter ion. Right? This one will have a cation that balances those charges. This one will have a cation that balances those. Those become spectators. For instance, if we had sodium dichromate, right, we'd have 2 sodiums here with that one. And we could do sodium sulfite with 2 sodiums here. Get those in solution, and they react. And they produce this chromium 3+ ion with a counter anion, and it could be this one. But what we've done here with this example is we've excluded the spectator ions. The spectators just get in the way. Right? So as long as you just recognize that there are spectators in there, in the real solution, if you were to do this in the lab, of course, you'd have to take that into account. But for performing this half reaction balancing trick, we only need the species that are actually participating in the reaction. So the first step, separate this one into half reactions. So I'm going to make myself a whole lot more room here because I know I'm going to need it. And of course, the slides in this set give you all these steps, but sometimes it's easier to follow along if you watch me do it on the board. Then the slides make more sense. So if we're given this one, dichromate, and then sulfite yields chromium 3+ and sulfate. Okay? And these are all aqueous. Sometimes you can have redox reactions in which a product or reactant for that matter could be in the solid phase, and that's okay. But in this case, all of these are in aqueous solution. So how do we separate it into oxidation and reduction steps? Well, you've got to know the oxidation state for each of the elements. Oxygen's not going to change. Not in this case. That's a 2 minus, that's a 2 minus, that's a 2 minus for oxygen. So really, the elements that are being oxidized or reduced are chromium, sulfur, chromium, sulfur. We just need to know which one. Now, the rules state that the oxidation state for this element is the charge, right? So its oxidation state is 3+. How about this one? Well, if we take that, 7 times -2 is -14. So that's the contribution of oxygen. And we have to balance the charge with chromium plus charges. But we need to reserve 2 minuses for the charge on the entire polyatomic ion. So that means we only need to balance -12 because 2 of them are up here. So that means 2 into that is -6. So we have to balance +6 for each one of these. 2 times 6 is +6, plus 12. Right. So these two are balanced. Okay, that means this chromium is a +6 oxidation state, and it goes to a +3 oxidation state. Right. So let's write this up here just to keep track of everything. That's a 6+ to 3+. So what has happened? Why did it go from 6+ to 3+? It gained electrons. It has been reduced. Right? So that means that this one, with its 6+, went to this one with its 3+. Reduction. Okay? So that means the other one has to be oxidized. So we have this one is oxidized to this one. But we need to know quantitatively how many electrons were transferred. Right? So if this one is 4 times, oh, it's Steffi again. 4 times 2 minus is 8 minus, or -8. Reserve 2 of them there for that charge. That means that this one has to be 6 pluses. This one is 3 times 2 minus, which is -6. Reserve 2 for that. We have -4, so this one is 4+. Okay. So this one had to lose 2 electrons to make that. Right. So let's just put those in there for later. And here we had to okay. For a single chromium, we had to add 3 electrons. We'll balance those later. All right, so let's balance the elements. So we have 1 sulfur, 1 sulfur. Everything except oxygen and hydrogen. 1 sulfur, we're good. And it's getting cluttered in here. Let me take those out of there. Okay. These, we've got 2 here. We need 2 here. Now we can go to the oxygens. So we balance oxygens first with water. So if we have 3 oxygens here and 4 there, that means we had to add an oxygen on this side. in the form of water. Okay, so now we have 4 oxygens, 4 oxygens. How about this side? Well, we got 7 oxygens here that have to show up on this side to balance them. So we need 7 waters here to give us 7 oxygens. Okay? So now we got the oxygens balanced. Now we need to balance the added hydrogens that we plugged in there with our waters. So here we have 2 hydrogens. We need 2 protons. That's how we balance those 2 hydrogens. Here we have 14 hydrogens on that side, which means we need 14 hydrogens on this side. Okay? So now we got elements, oxygen, hydrogen. Now we can balance the electrons. So if we've got 2 electrons here, and well, actually we don't have 3 electrons here. We have 6 electrons because 3 went for each one. So that becomes 6. All right. So 6 electrons are balanced for this one. 2 electrons are balanced for that one. Now we need to do whatever is necessary to balance the electrons between the 2 so that we can add them together. So this is 6 electrons. We need 6 here. That means the whole thing is multiplied by 3. 3 times 2 is 6. 6 electrons on this side, 6 on that side. Now we can add them together. So we've got 1 dichromate here. We've got 3 sulfites. Okay. We've got 1 water. And we've got 6 electrons. Okay. On this side, we've got 2 chromium 3 plus. Let's come down here. We've got 1 sulfate. We've got, let's see, let's keep them in order. 7 waters. And 6 electrons. Okay. Hydrogens. I left out hydrogens. 14 hydrogens. And 6 hydrogens. There, now we've got everything. That one, water, electrons, hydrogens. That one, water, electrons, hydrogens. Okay. Now you cancel whatever you can. So, there's nothing to cancel here or here. Waters, that one's gone and leaves us with 6 here. Electrons are gone. Hydrogens, these are all used up and you have 8 left over here. Okay. So, instead of bringing all that down, let's just go to the end product here. And this is what we should have left. 1 dichromate, 3 sulfites, 8 hydrogens, and on the product side, 2 chromium 3 pluses. 4 waters. What did I do wrong? Three waters. Right? 3 times that, 3 waters. So that means 3 from 7 is 4. 4 waters, and that's it. Now we're balanced. Okay, that's the method of half reactions for an acid-based solution. And you will usually have some hydrogens left over here to show you that it's acid-based. Now, something to keep in the back of your mind, or in your left hip pocket, or wherever in your purse. Once you've done this balancing act, it's good to note in the process how many electrons were transferred. In this case, 6 electrons were transferred. In a later equation that we're going to study in a few minutes, we need to know that 6 electrons is equal to an N that goes into the equation. Right. So you keep that back here. Even though it disappeared in the overall equation, they were actually transferred, 6 electrons. Okay, we need to remember that for using the Nernst equation later. Okay, any questions about what I did, how I did it? This method is good for one thing. You just do it step by step by step. You get to the end and you're done. As long as you don't make mistakes like I did. Okay. So let's clean off the battlefield here. Make room for the next one. And I guarantee the review document has several of these for you to practice with. Let's see. I'm gonna keep closer track of what I'm doing and where I'm at in the process. Okay. All right. Let's do this one. Let's balance this one in acidic solution. And then I'm going to use it to show you basic solution balancing. Okay, so if we have one bromine ion, these are all aqueous solution, except for Br2, which is a liquid. MnO4 minus yields bromine to liquid and manganese. Okay. So what do we do first? We have to find out what the oxidation states are. This one's fairly straightforward. Oxidation state here is -1. Oxidation state on an element in its natural state at standard temperature and pressure is 0. That's the oxidation state for bromine. This one is -1. This one is 2+ for manganese. This one's the only one we actually have to calculate. So oxygen times 2-, 4 of those is 8-, right? Or -8. We need to reserve 1, so we only need to balance -7. So this one is 7 pluses. Okay, now we can split them up. We know that this one went from -1 to 0, which means it lost an electron. This is the oxidation reaction. So bromine there to bromide to bromine here is our oxidation. Reduction then would be the other one. Okay. So we balance our elements first. 1 and 1, no, 1 and 2. We need 2 of those. 1 and 1, that's good. Now we balance the oxygens. There are no oxygens in this one, so you're done. But this one, we have 4 oxygens on that side. We need 4 on this side in the form of water. And we placed 8 hydrogens there, so we need 8 hydrogens here. Okay, we've done elements, oxygen, hydrogens, now electrons. So if we lost 1 electron per bromine, then for 2, we had to lose 2 electrons. Remember, oxidation, electrons go on the product side. This one, we went from 7 pluses to 2 pluses, which means we had to gain 5 electrons for each manganese. Right? So we only have 1 manganese. That means we gained 5 electrons. Okay? So now, I'm just checking myself. 1 manganese, 4 oxygens, 8 hydrogens. Okay, that's good. All right. So now we need to balance the electrons between the 2 so that we can add them together. What do you do when you have an even and a prime number? Cross multiply. So you multiply this one times 2 and this one times 5. That'll give you 10 electrons here, 10 electrons there. So we have 10 bromine, or bromide, excuse me. We have 5 elemental bromine, and we have 10 electrons. And this one we have 2 manganate ions. We have 16 hydrogens. We have 10 electrons. By the way, N equals 10 electrons. Just for later, if you need it. 2 times this, manganese, 2 plus, and 8 waters. Okay, now that we've got our electrons balanced, 10 on that side, 10 on this side, we can combine the equations. So let me see how much we can do before we actually write it down. We can get rid of the electrons. Right. We've got no hydrogens and no waters up here. So everything comes down. 2 manganates, 10 bromides, 16 hydrogens. Okay. Takes care of this side and this side. Now it's this side. We're going, let's put the manganese first. Okay. Then the 5 bromine. Then 8 waters. Okay. So let's see. Can we reduce this any further? 2, 10, 16, 2, 5. There's no way we can reduce that any further. So that should be the balanced equation. Just checking my work. See if it agrees with the slide. Yep. Okay. So that's our balanced in acidic solution. Now, stream of consciousness. We have some slides after this that describe the basic solution method. But I'm going to use this one because the basic half reaction method is what I call fake acidic. You do the acidic first, then you change it into a basic solution. right? So I'll show you how to do that. So we'll take this equation and keep it. This is the acidic balanced equation. Now, the oxidation reductions have not changed, right? It's the same oxidation and reduction as the acidic, but now we're changing the character of the solution to basic. That's all we're doing. All right. So that I don't have to write it all over again, I'm going to make my changes going that way. All right, so how do you turn this into a basic solution? You consume the protons with hydroxyls. Right? So if we've got 16 hydrogens, how many hydroxyls do we need to add to consume all of those? We need 16 hydroxyls. So if we add 16 hydroxyls to this, got to add it on both sides. We can't just add it one side and not balance it on the other. So on this side, we add 16 hydroxyls. Okay. Now we combine these, and that makes 16 waters, right? H2O. And on this side, they're just hydroxyls, right? So let's move these up here to MnO4 minus plus 10 Br minus plus 16 water. Okay. That's the reactant side. Now the product side. I'm going to move the product side down here. We still got our 2 manganese ions. We've got 5 bromine molecules. We've got 8 waters. And we've got 16 hydroxyls. Let's see, did I count for everybody? There. There. These are waters. There. There. Okay, so that's everybody right here. Now you cancel anything you can. So we've got 16 waters on this side, 8 waters on that side. Those are all gone. These become 8. So now you have a balanced equation in a basic solution. And there's the proof that it's basic. There's your hydroxyls. Okay, any questions? That's my fake acid method, half reaction method. Theoretically, you could start from scratch and balance an equation in basic solution, but it would be extremely difficult and prone to mistakes. So I think going the acid route, then converting to basic is probably the prudent way to go. All right, so our subsequent slides, this is my fake acid method. First you balance it in the acid solution, and then you consume the hydrogens with hydroxyls. And then finish balancing however you need, canceling those things that you can for reactant product side. And this is the modified decision schematic for the method. Down to here with this sort of bluish purple is still acidic. Then when you get to the green, that's when you shift into basic drive. Okay. Oh, okay. What if you started by adding hydroxyls first instead of hydroxyls? If you were to approach this as a half reaction basic from the beginning, then you would have to add hydroxyls somewhere, right, instead of hydrogens. So what potential problems could you encounter? Well, you have to add water on the other side to compensate for the oxygen in the hydroxyls. That's one way. And then you have to balance the both oxygen and hydrogens by the addition of water. And now you've got hydrogens on both sides. With the acid method, you've only got hydrogen on one side in addition to the water. So it becomes a little easier to balance. It just gets really complex. Okay, let's see. I've got something sitting in the way. Let me see here. Okay. So what are we going to do here? Balance the following oxidation reduction reaction occur in basic solution. We just did one, so we could follow along with the slide. Right? This is the result that you should come up with. What do you have to do? You have to decide which one's oxidation, which one's reduction. Yeah, we've got time to look at that part at least. So if you have cyanide on one side, and then the manganate ion, we already determined what this one was, right? +7. How about this one? Well, in this case, we've got to decide what's the product, because we don't know whether it's carbon or nitrogen. One or the other has been reduced or oxidized. So we have product and this. So we need to know what this one is. So that's 4 minuses here. Since it's neutral, you got to balance all 4 of them, 4 pluses. So the manganese goes from 7 to 4 plus. That means it was reduced by adding 3 electrons. So the reduction equation involves this one. Right? Okay, so that means the oxidation has to be this one. So we're going to have some electrons over here. And we're going to have 3 electrons here, we know, for that manganese. The trick is to decide whether it's carbon or nitrogen that was oxidized or reduced. When you have to choose between the two, it's usually the carbon that changes its oxidation state. Now let's see if that makes any sense. If that's true, what is nitrogen in this situation? Well, nitrogen is here. Nitrogen's there, right? And typically you have a -1, -2, -3 for nitrogen. So if that's the case, and we have -3 here, that means we only have to balance 2 of them, because we've got to hold 1 minus for that. So that would make this 2 plus. In this case, we've got 2 minuses here, 3 minuses there, which is 5 minuses. Hold 1 for the charge, 4 minus, this is 4 plus. So that fits the scenario. We went from 2 plus to 4 plus and lost electrons. Right? So 2 to 4 means we lost 2 electrons. One of the reasons that we opt for nitrogen as constant in this case is because of the position on the periodic table. Notice where carbon is. Carbon is smack dab in the middle between the minus valences and the plus valences. So carbon could go either way. Whereas nitrogen is more likely in this situation to be a 3 minus. because of where it's positioned. Since carbon is in the middle and it has a lower electronegativity than nitrogen, then it's less likely to be a constant valence. So that's why we say nitrogen is 3- here and here, and let carbon be the reduction. All right, so then we would need to go through our procedures for balancing the acid solutions, right? You would have 2 of these oxygens end up over here. Right? That means we have, well, we balance the manganese. Carbon, nitrogen, they're balanced. The 2 hydrogens gives you, 2 waters gives you 4 hydrogens here. So we'd have to add 4 hydrogens there. On this side, we need to add water on this side. 1 oxygen. So we've got 2 hydrogens here, like that. Then we would have to balance the electrons. We've got an odd and an even. So that means cross multiply. 3 times this one, 2 times that one. Then once we get to the balanced equation in hydrogens, you just neutralize them with hydroxyls, and this is where you end up. You can verify that one on your own. I think the trick to this one was deciding which one of these, carbon or nitrogen, was oxidized. All right. A galvanic cell. I called it an electrochemical cell earlier. Galvanic cell is a synonym for that. In fact, galvanic is historically proper. It's named after an Italian guy by the name of Galvani. You know he's Italian because his name ends in a vowel. And these devices are used to change chemical energy into electrical energy. And that just means in a chemical reaction, electrons are transferred, and all you need is an engineering solution to capturing those moving electrons. Right? In these reactions that we've described previously, everything was in the same bucket, in the beaker, and the electrons were transferring at will. We had no access to them. There was no way to extract energy from the movement of those electrons from one place to the other. We know there's potential energy involved because if you measure the temperature of these solutions before and after, you find that the transfer has increased their temperature. So they've released energy in the process. And the reaction is spontaneous. And we're going to talk about that too. In these reactions, how can we determine a spontaneous reaction? Okay, so this device is a method of capturing that electrical energy that's being transferred as the electrons move. So here are possible solutions. In each one of these cases, you have 1/2 reaction on one side, the other half reaction is on the other side. So we separate the half reactions and we give them an external pathway for the electrons to travel and the ions to be exchanged, right? So the electrons are transferred through this wire, one side to the other. We don't know yet. And then because the electrons are moving and creating an imbalance in negative charge from one side to the other, we need another route for the positive ions to move so that we can balance those charges. Right? In physical terms, I don't know if any of you have had physics yet, but when you talk about an electric circuit, the circuit means that you have to have a pathway for electrons, for the current to move in a circle. It has to be complete in a circle, so to speak. Right? So if we pull that salt bridge out, reactions would stop. Or if we disconnected this wire from one side or the other, no reactions. Okay, you have to have a circuit. That's why the external wire is balanced by either a salt bridge or a porous disc or some other method that allows movement of some ions to balance the charge without actually mixing the half reactions on either side. That's a galvanic cell. We just have to decide, how are we going to construct it so that we put a half reaction on one side, oxidation on one side, reduction on the other. Okay, this just describes the purpose of the salt bridge or the porous disc. If we were to do this in the lab, we would get some auger, right? Everybody knows what auger is. It's a very complex polymer that's derived from natural sources, usually seaweed. And it's used to stabilize a solution, lock it in place. It's kind of like Jell-O, only it's not Jell-O because Jell-O is a protein. Okay, and I've used both methods. I've used auger and Jell-O or protein in this salt bridge, and the protein always gives you trouble. The protein tends to interact and add to the reactions that are going on, and it confuses the issue when you're trying to measure voltages. So I got away from that one pretty quick. So you need to use auger to stabilize that solution, the electrolyte that's in the salt bridge. And it could be 1 molar KCl, that's common, right? Or if your reaction is using sulfide ions, sulfate in solution, perhaps, you may use this one. That will work. So you look for compatibility as well. But when in doubt, potassium chloride is a good place to start. And that allows for transfer of charge and completes the circuit. Or you could have a porous disc. The porous disc is more efficient because the ions have to travel less distance through a disc than they do through a salt bridge. Right? So you'll be closer to, when you measure the voltage on your cell, the voltage will be closer to the theoretical because the porous disc offers less resistance to the movement of ions. Okay, so more terminology, but this piggybacks on the oxidation reduction we've already learned. The anode is the side of the half cell in which oxidation occurs. So anode implies oxidation, and the cathode implies reduction. Okay? I don't have an acronym for that one. But if you look at what reaction is happening on this side, and we normally, when we when we draw these out like this, we put the anode on the left-hand side. It's not always the case, but it's a good convention to follow. And I'll explain why in just a minute. So if we put the anode on the left, that means oxidation is occurring. So what do we mean by oxidation? Something is losing an electron, right? So where do those electrons go? Those electrons go into the electrode and across the circuit, right? So in order for something to be oxidized at the anode, you have to transfer electrons out of that solution, okay, into the external circuit. And then, of course, just like oxidation and reduction occurs in pairs, anodes and cathodes are in pairs. So those electrons go over to the other side where reduction occurs. So those electrons are added to something on the cathode side, and they're consumed as a reactant. Okay? You can think of it this way. The cathode here has something with a positive or a more positive oxidation state. Remember what a cation is. A cation is a positive ion. Now that doesn't mean that you have positive ions on this side, but very often you do at the cathode. And those positive ions now are going to combine with electrons and be reduced at the cathode. So that wherever the cations occur is the cathode side. And they're being changed by addition of electrons. I don't know if that helps any. May just be better to memorize them. Cathode is reduction, anode is oxidation. All right. So now let's talk about cell potential. Both of those half reactions together are the galvanic cell. You have a half cell and a half cell combined to make the galvanic cell. And when you have completed the circuit, you should be able to measure a voltage in the external wire. That's called the cell potential. And the unit of measure is the volt. Okay? So that's good enough for now. We'll continue discussing. You can think of the cell potential as a push. Right? So if you have your anode and your cathode, and your external wire and your salt bridge, okay, then you're going to have electrons moving this way, and you can measure a voltage on a meter. Okay. That voltage represents a push. When I hear volt, I think push. Something is pushing those electrons from one side to the other. And that volt represents an electromotive force. It actually is a method of expressing a force. Okay, so what does a volt mean? Well, we have to introduce some other units in order to do that. We already know what the joule is. Right? Joule is our unit of energy. But there's also a unit for charge. How much charge transfers or is contained, if it's electrostatic, how much charge is contained in a conductor, or how much is transferred from one place to the other, is a coulomb. Now, you just have to accept coulomb as a unit of charge. It comes from the early 19th century. Engineers were trying to come up with units of measure that were convenient, that were practical to use as they developed their devices. One in particular was the transatlantic telegraph cable. So they got together and they butted heads for a while, and they came up with a unit of charge, and they defined it, some form. And that's good enough for now. But when you combine these values, the volt, the coulomb, the joule, they are related a certain way. So if we say 1 joule of work, right, so much energy, per coulomb of charge transferred is a volt. Right? So we can write an expression for that. So 1 volt is equal to a coulomb of charge transferred for every joule of energy expended. And you can rearrange that for however you want. So that would mean a coulomb would actually be volt joules. So you get your conversion factors there if you need them.
Watch the gray metal ions in solution. At the cathode, metal ions reduce by gaining electrons from electrical current in the electrode. Metal atoms deposit on the cathode as metal ions in solution move toward the cathode and encounter electrons there.
Okay, this is an example of a half reaction which involves a solid as a product. Right? So if you have metal ions in solution and they're reduced, well, they're not metal ions in solution, they're metal ions. Their source is metal. Metal ions in solution, if they're reduced, they would be positive. If we add electrons, neutralize them, then they tend to be a solid. So they accumulate at the source of the electron flow. So the electrons are coming out here, combining with the metal ions and forming a solid. So the solid element of the metal would be a product in this half reaction. Let's see. Next one.
Watch the gray tip of the metal anode on the left. At the anode, metal atoms oxidize to release electrons, which flow as current through the electrode. Positively charged metal ions enter the surrounding solution. The metal ions move toward the salt bridge.
So this is, in some sense, the opposite. In this case, we have a metal electrode, and the metal is being reduced. So the electrons are being drawn up through the electrode into the external wire and leave behind the metal ion that has lost an electron, and it goes into solution. So this is a case when you combine these two half reactions where the electrodes are participants in the reaction. So on the, this is the anode side. The mass of that electrode should decrease over time as the reaction proceeds because you're losing metal ions into solution. On the other side, you're precipitating metal ions from solution on the electrode, so that electrode should increase in mass. This is a convenient way to describe a galvanic cell at the beginning, where the electrodes actually participate in the reaction. But the fact of the matter is, you don't have to have the electrodes participate in the reaction. The reaction can occur entirely in solution, as was our earlier example of the dichromate becoming chromium 3+, right? You don't form any metal there, any solids for either the oxidation or the reduction. So what do you do in that case? Well, all you need is a conductor in solution. Right? You just need something to conduct the electrons away. And a good choice, at least in the laboratory, a good choice is platinum electrode, because platinum is not part of the reaction process. And it's inert. It doesn't corrode. I said you use it in the laboratory because platinum is expensive. So maybe to save on cost, your electrode might be platinum coated. It could be something cheaper underneath, but the surface would be platinum because it's inert. Some reactions use a carbon rod. Batteries that you buy in the store, dry cell batteries, the C's, the D's, the AA's, the AAA's, they all have a carbon rod right in the center. Okay, so let's look at some more definitions. How do we measure this cell potential? Well, you need a device that's calibrated so that when a force is being applied through your external circuit, the instrument can detect that force by movement of electrons. And there are two different ways to do that. One is called the voltmeter. The voltmeter has a standard resistance built into its circuits, and it uses the measurement of current.
About your prescription order ready for pickup.
It uses that circuit with Ohm's law. Let's see. I always remember it this way. Voltage equals current times resistance. That's one version of Ohm's law. So if this is constant, then we could put it on one side and then solve it for this, right? So this would be V over I. Right? So if your circuit has a constant reference resistance, then if the current increases, you measure the current through your circuit, then you know the voltages, and they go together. So they're calibrated by this constant. That's a voltmeter. A potentiometer produces the same results. It gives you a voltage, but it does it differently. So a potentiometer has to be in the circuit, right? So you have your here, here, and your electrons are moving this way. And your potentiometer then is in here, between the two. And what it does is it has built into its circuits a way to oppose the force. So it sends electrons back this way until there's no current, nothing's moving. Then it takes whatever was required to do that and spit that out as a voltage. So it's a measured opposition potential. That's why it's a potentiometer, because it uses a potential of its own to oppose the external potential. And when they're balanced, then it interprets that as a voltage. Right? I think the voltmeters are cheaper to make. So if you go to the store and buy a meter, it's going to be the first kind, the voltmeter. But if you want a very precise measurement to several decimal places, the potentiometer works better. All right. So here we have a digital voltmeter that is measuring the voltage between the two. And for argument's sake, I think the left one's going to be the anode, the right one's going to be the cathode, and we have a porous disc this time instead. Oh, that just shows you what you do, how you put it in circuit. So if we were to build a battery in the lab, we would do it this way. We would have our anodic solution reaction over here, half reaction, cathodic over here, and our voltmeter would be between. If you want to stop the reaction, just pull one of those plugs, and the reaction stops because there's no longer a circuit. Okay. Now, it would be convenient and very useful if we could balance our reaction and then use that reaction, the values that are obtained from the balancing process, to calculate a theoretical voltage for the reaction. And that was on chemists' minds from the beginning. The problem is, these two reactions, the oxidation and reduction, always occur together, right? So there's no way to get at what the theoretical potential would be. So some smart person came up with, well, all right, if we have to have an oxidation and reduction together, let's just compare all existing oxidation and reduction reactions separately with a standard reference. Right? So they came up with a standard reference, which turns out to be the standard hydrogen electrode, or standard hydrogen reduction. Okay, that becomes 0 volts for that half reaction. So we would go from this to this in solution. And that was arbitrarily given 0 volts for that transition. Okay. Now, this would be, let's see, that would be an oxidation. Right? So if you take this oxidation reaction and compare it to all other reactions in terms of their reduction, then you measure a potential for each of those reductions. So something like something that would be reduced, say silver plus an electron, would give you silver metal. Okay, compare this one to that one, and then whatever you measure is attributed only to that half reaction. Now we've got a way to reference these two. You've got standard reduction potentials for all of these reduction reactions. And your book has a chart with all those in it. The review document has at the end a reprint of the standard reduction potentials. And I've got, for the exam, in the folder for the exam is a a document with the standard reduction potentials right there. So you've got all that information. We just need to know how to use them. Now that we have a standard for each half reaction, you can compare two half reactions, one as an oxidation and one as a reduction. Because if you compare this one to that one to that one, you can compare the two together. Okay. So these are the standard conditions, right? All solutions are 1 molar. Any gases that are in contact, that are used, like this one, that gas would be 1 atmosphere pressure, okay? And the temperature would be 25 degrees centigrade. Those are standard conditions. Each one of these half reactions in the table is given a voltage, is assigned a voltage based on standard conditions, right? So you would have so many volts here. It could be positive, could be negative. If you invert the reaction and change this to an oxidation, then you just change the sign on your standard potential. If you use it as a reduction in your galvanic cell, then you just keep the voltage as is, positive or negative, doesn't matter. Okay? Now, let's see. There's part of the chart right there. So each one of these is assigned a voltage, positive voltage. There, 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 there. Then here's your standard reduction for hydrogen. Would be that one. Would be 0. So notice that if you flip this reaction, it's still 0, right? So the standard for the hydrogen electrode is 0, whether you run it as an oxidation or a reduction. And then down here, you get into negative voltages. Let's see, here's the rest of the table. Okay, so what do you do with it? Well, the authors of the book and most diehard chemists just memorize this formula. So the potential of the cell is just the standard reduction potential for the cathode, which is where the reduction occurs, right? So it's going to be a reduction. And the standard potential for the anode in reverse. So you take the negative sign of it. Then if you're then if you combine those numbers, you get a standard potential for the cell. All right, so here's the key. If the reaction is going to proceed as written, with the electrons flowing from the anode to the cathode, the standard potential must be a positive number. So a positive potential for your cell means spontaneity. Remember, the delta G has to be negative, but the voltage has to be positive. Okay. What do you do if you're combining two half reactions and you have to multiply one by a constant in order for your reactions to be combined? Does the standard potential change? No, it remains the same. Why? Because that is an intensity factor. it doesn't matter how much you have on either side. It remains the same. Voltage is an intensity, not a capacity factor. Okay. All right. So if you want to, you can just say, all right, we wrote it as an anode-cathode reaction. I take the cathode, subtract the anode. What do I get? All right. That's one way to do it. I prefer taking your half reactions, looking at their standard potentials, and then say, all right, if we turn this one into an oxidation, which would be the anode, we flip it. This becomes negative. Then add your voltages together. This small negative plus this large positive means that your voltage is positive. And that means that if you make this one the cathode and that one the anode, then that's going to be spontaneous, because the combination of them then becomes a positive value. Let's see, on the next page, I guess. Here we go. All right, so then if you see, this method helps you determine which one should be the cathode and which one should be the anode. Right? The other way, if you just memorize the formula, you may get it wrong the first time, which is okay. If you call one the anode and the other one the cathode, then you change the anode's potential because it's oxidation, and add them together. If it's negative, that means you just need to flip the reaction and make the cathode the anode and the anode the cathode. Right? So either way works. This just follows a logical flow better for me. If you look at the two reduction potentials here, and you say, which flip would give you a positive value? If you change the first one, the iron, into an oxidation, it gives you a large negative number, and the combination is negative. So that won't work. You need to change this one into the anode. Okay, that's the way I approach it. And under standard conditions, the voltage will be 0.43 no matter what you do to balance the equations. Right? If you multiply times 2, the standard potential does not change. It's an intensity property. Now, this voltage is under standard conditions, where these ions here, let's see, here and here and here are all 1 molar concentration. And of course the solids, they don't change concentration. And we have no gases, so pressure doesn't matter. Temperature is 25 degrees. This is the voltage you should expect under those conditions. But we rarely set up a galvanic cell under those standard conditions. It's usually a lower concentration. So we need a method to convert this voltage into the actual voltage where we don't have that little zero right there. The actual electromotive force, electrical potential. Okay. Let's see. I've introduced the word Nernst equation here, but I haven't defined it yet. Right. So we need to do that. In order to determine the true voltage on your cell, you need to know the concentrations of your anode and cathode solutions, and you need to know the number of electrons that are transferred. Right. The moles of electrons that are transferred in the balanced equation. That's why I wanted you to hang on to that value from earlier. Okay, all right. I thought I was getting to the Nernst equation, but it's going to take us through some other things here. But I think we might run out of time before we get there. Unless, all right. So here's another concept. Remember what an oxidizing agent does. An oxidizing agent must be reduced because it is responsible for oxidizing the reactant in the other half cell. So the strongest oxidizing agent is the one that is most likely to be reduced, or the most easily reduced. Okay.
Dr. Bly.
Yeah.
Before I forget to tell you, I took my chapter 14 and 15 test this morning.
Yeah.
I took it twice.
Okay.
So I had the option to take it 2 times. I think I did a lot better the second time I took it.
Okay. So the score that I've got in my books now is the first one, isn't it?
Yeah.
And you probably took it after I recorded. Okay, I'll go in and check it and
Okay.
Okay. Okay, so how do we determine which one is the strongest oxidizing agent? Well, the one that has the largest reduction potential. The most easily reduced will have the largest positive toward the positive. It could be negative, but the largest on the positive end. So what we need to do is write the reactions. These are our reduction potentials for these guys. Right. So there's the F minus. There's the sodium. There's the sodium plus. There's the chlorine, and there's the iron. All right. So these are written in terms of reduction potential. So we should be able to organize these from most positive to least positive. Right? The most positive is this one. But we're looking at that species, F minus. Right? So in order to do that, we've got to reverse this one and put the F minus as a reactant. Because if we're assessing the ability of an oxidizing agent, it has to be a reactant because it's combined with something that needs to be oxidized. So we got to flip that one. All right, that gives a negative. How about this one? Sodium, yeah, sodium's there. So we need to flip it also for this one. Okay, so now we've got both of them, sodium ion and sodium metal. So we've got these to compare. That's why I put them in blue so we wouldn't mix them up. That one has to be reversed because we're looking at this one as a reactant. And this one has to be reversed for iron to be a reactant. Now we can put them in order. Largest, most positive would be sodium. It's the most, the strongest oxidizing agent is the most easily reduced. Okay. So there you go. That's the order. Okay. Line notation. All right. So remember I said the convention was to put the anode on the left, cathode on the right when you're drawing your pictures. Line notation is a shorthand way of expressing what's happening in those half cells. Okay, so we put the anode components on the left, the site of oxidation, and the cathodes on the right. And we separate the two by a double line. The double line represents either a porous disk or a porous disk or a Mine's gone blank. Salt bridge. Okay, so the anode's going to be on this side, cathode's on this side. Now we need to know what order do things come in on this side. We want to include the concentrations, but that's after you get them written up there. So what happens on this side? On the anode side, you're oxidizing, correct? So in this case, we're going from magnesium metal to magnesium ions in solution, right? This represents a salt bridge or a porous disk. This represents a change in phase, right? So this phase changed from solid to aqueous. And it happens in order of the reaction. So for this one to be oxidized, it goes from here to here. Electrons are lost. They're headed over there. Okay. On the other side, we want reduction in the order that it occurs. So in this case, aluminum 3+, phase change, aluminum metal. Okay, so in this case, at the cathode, aluminum ions are reduced to aluminum metal because electrons are supplied through the bridge to this side. Okay, and then you would put the concentrations in there. Standard concentrations, that's a solid. 1 molar, 1 molar. If it happens to be something different, whatever that happens to be, you want as much information as you can put in there that will describe the cell. And concentration is very important. So here's what I was referring to earlier. If you need an electrode just to transfer electrons, but it doesn't participate in the reaction, then you pick something that's inert, like platinum. And here's the case where you would need an inert electrode because the reaction occurs entirely in solution, right? Let's see. So there's what we've decided is a cathode. This is our anode. Now, let's say, is that correct? The voltage for iron 3+ to iron 2+ reduction is plus 0.77. So when we reverse it, the sign changes, and if you add those together, you still get a positive voltage. So that is correctly written. This is the cathode. This is the anode, oxidation, reduction. And this is the equation for the balanced cell. Let's see. That's what I just said. We're going to write line notation here. That's what I was hoping for. Doesn't look like it. So what do you do if you have if you don't have a phase difference? Let's say for argument's sake, we have, what was it, iron 2+ and iron 3+. That's the wrong side. It should go on this side. So iron 2+ to 3+ would be the anode side. Put a comma. And then you need your platinum electrode. That is a phase change. So this is the reaction from on that cathode, the anode side, with a platinum electrode providing the conduit for electrons. Okay. Now let's get to, okay, I put it on the wrong side. My mistake. The platinum electrode comes first in a phase change, then the reaction. Let's see. So here's our galvanic cell. That's nothing new. So this is an example of a copper and silver electrodes in, and notice that the solution has to have copper ions in here, silver ions in here, in order for the reduction to take place on this side and the oxidation to take place on that side with a salt bridge. So what happens what would happen to the potential if you increase the copper concentration on this side? But the short answer is the potential would decrease if you increase the amount of copper on this side. So why is that? Well, let's look at it. Well, okay, here it is written. So this is the reaction on the anode side. We're oxidizing copper, right? If you increase the concentration of copper here, then you drive the reaction back toward that. And that decreases the tendency for oxidation. Right? So the overall potential would decrease if you increase the voltage. So if you decrease the concentration of copper, you would increase the voltage. Okay? I wonder, could we start this reaction with no copper over here? Like just pure water? Well, it wouldn't be pure water. We'd have to have something to conduct. So let's make the copper concentration just infinitesimally small. You theoretically would increase the voltage. Well, I say infinity, but that's not possible. It would be very large. You'd probably reach a point of diminishing returns. Okay. So, so now we're going to switch gears a little bit. We're going to say, remember initially we were talking about these reactions occur in solution, and we were trying to get at that potential energy that was being expended in the movement of electrons, right? So it would be nice if we could take that voltage and convert it into some value of work, so we could compare it to, you know, how much work can we get out of it? So this is the conversion, right? And the voltage is equal to the amount of work divided by the transfer of charge, how much charge is transferred, right? So work is going to be equal to the voltage times the charge. And notice we've got a negative sign here. That's because everything is in terms of the system. Right? So if we're saying the system is doing work on its surroundings, that means it's losing work. So that's a negative value. But in order to get work to be done by our galvanic cell, the potential, the voltage has to be positive. Right? So in order to for sign convention, we have to change the sign. So if the work being done is equal to how much charge is transferred times the voltage involved, the signs won't match. This sign needs to be negative in order to be working on surroundings or extracting work from the system. So that's why we put a negative sign there, and it's simply to maintain the sign convention of everything we do in terms of the system, what happens to the system. Right. That's the sole purpose of that negative sign. Now, as we know, second law of thermodynamics says well, first law says you can't get something for nothing, right? Delta E for the universe is energy, that is, not voltage. Delta E for the universe is 0. But second law says you can't even break even. You always lose something in the process, right? And for a spontaneous reaction, that means that you increase the entropy of the system in order to do it. So this is the theoretical maximum work that can be obtained from that cell. We know that the actual work will always be less. Okay, so if this is our equation, the work in joules, the Q is our charge, and E is voltage. What are the units for Q? Well, the Q is a quantity of charge in coulombs, right? We mentioned that earlier. So this is going to be in joules. This is going to be in voltage, volts. This is going to be in coulombs. So 1 joule is 1 coulomb volt, or 1 volt coulomb. But many reactions we want to be able to quantify in terms of moles of reactant converted from one to the other. Say we want to convert, we want to plate out silver on a surface from a solution. In order to do that, these are molar relationships, right? They have nothing to do with, no direct relationship with coulombs or volts. So we need a conversion factor that will convert the charge transferred into the number of electrons transferred. Now we have a handle on this oxidation reduction process. And that conversion factor is the Faraday. 1 mole of electrons is equal to 96,485 coulombs. Okay, so that's your Faraday. And that value is given in useful information at the end of your review document. It's also that useful information is given in the folder where the exam is located. So you don't have to memorize the number. You just need to know where to find it. All right. So now we know that the maximum amount of work is equivalent to Gibbs free energy. That was the whole purpose of Gibbs doing this work with his equation. Remember where he said, when Gibbs said the change in free energy is equal to the enthalpy minus the temperature times change in entropy. So this represents the maximum useful energy available from a reaction. And that maximum useful energy is equivalent to the maximum work that can be obtained. So that's why we say that the amount of work, the maximum amount, is equal to the change in Gibbs free energy. Okay. So if this is equal to that and that's equal to that, right, the commutative property, this is equal to negative Q voltage. Okay, electrical potential, electromotive force. So now we have a relationship. If we measure the amount of charge transferred and the voltage at which it's transferred, we can calculate Gibbs free energy for that reaction. Right? So we have another way of measuring Gibbs free energy. I think last chapter, we used the equilibrium constant to do that calculation. And now we have another way to get the Gibbs free energy. All right, also, the number of coulombs is equal to the number of moles of electrons times the Faraday, right? Because the Faraday is 96,485 coulombs per mole. And if you have the number of moles, that cancels moles, and that gives you coulombs of charge. So we could substitute this one in there. Number of moles of electrons times the Faraday times the electromotive force will also give us delta G. Oops, left out the minus sign. Here we go. Okay. So what that means is if the reaction is spontaneous, delta G has to be negative, which means that E has to be positive to give you the negative of the term. Okay, that's why I said earlier that a spontaneous reaction in electrochemical terms is a positive voltage. All right, so I'm running out of time as usual. Let's see. The concentration cell, we have to cover this. What would happen in an electrochemical cell if you had both electrodes, the same material, and the half reaction on both sides was exactly the same? Well, under standard conditions, there would be no driving force for the electrons, right? Because you'd have the same reaction on both sides. But if you change the concentration, remember what we said, if you change the concentration, Le Chatelier says you're going to drive the reaction toward the lower concentration, right? Remember that? If the anodic side is the oxidation side, then this yields that plus this. If we reduce that silver concentration, we're going to drive the reaction this way, which gives up more electrons. Okay? So by comparison, this one, the lower concentration becomes the anode, and the higher concentration becomes the cathode. That's a concentration cell in which both half reactions have the same components, but one runs as an oxidation and the other runs as a reduction. Now you may have already guessed the voltage for this process is going to be very low, in the order of millivolts, but it does happen. And actually, if we were to do this in the lab, I'd prove it to you, because that was one of the things that we would have done, set up a concentration cell. Okay. Now we're at the Nernst equation. This is the equation that allows us to calculate the actual voltage or the electrochemical potential for a cell based on its concentration, right? We're no longer at standard potential. So the Nernst equation is this one. The actual potential is here. The standard potential is there, so you do need to know that. And you have to calculate that from your two half reactions. Then this is your gas constant. This is your temperature. And the temperature has to be in Kelvin. And this is the Faraday constant. And there's your N, the number of moles of electrons transferred in the oxidation reduction reaction. That's why I wanted you to hang on to that one. And then the natural log of the Q. Why did we say Q? Because if we used K, the whole system would be at equilibrium and you'd get no voltage, right? So we have to use Q, right? And in order to calculate Q, you have to have the balanced equation. All right, that is the raw Nernst equation. But for convenience, we can combine some of the terms. Let's say of course, R is a constant. Let's say that we always conduct our experiment at 25 degrees. Right? So we can just put 298 in there for K. Faraday's a constant. All we have to do is insert the number of moles. But we also want to get rid of that natural log. Right? Natural logs don't behave well. And if we have a Q here that's calculated in scientific notation, it would be useful if we used common log. Right? So we do conversions and we insert information in here, standard conditions, and this is what we end up with. Okay, there's your constant, there's your temperature, there's your Faraday, and here's your conversion for the natural log. 2.3026 times the log equals the natural log. Right? Just take my word for it. Then if we reduce all these other values into one constant, this is the Nernst equation that we typically use. 0.0591 in the numerator, number of moles of electrons transferred, the common log of the Q. That's the one that's useful for most people. You would only need to use this one if you were going to change the temperature usually. If you change the temperature, then you would have to make that your base equation. This is just a proof of the conversion factor. You know, take my word for it, or run through that proof, and you'll see that I wasn't lying to you. Okay, got 5 minutes left. As usual, if you have to leave, if we run out of time, you have to leave, and I'm still talking, I'll just finish the recording, and you can look at the rest of it later. So, what if we are at equilibrium? Then electric potential is zero, right? There's no driving force to produce an electrical potential. So if Q equals K, and we substitute K in here, that means the true voltage is equal to zero. But of course, the standard potential is still the same. So if we make that substitution, then we can calculate the K value based upon the measured or the standard potential. All we need to know is how many moles of electrons were transferred. So there we have a way of relating the electrical potential of a reaction to its K value. So there's another way to get your handle on K. Or if you know K, you can calculate this one. But usually it's the other way around. You can measure this one and then calculate K. Okay. So here's an example where we have a balanced equation, I think. No, that one's not balanced yet. So we find the half reactions. We find the voltage for the half reaction. If we write it, which way would we flip it to get a positive voltage? If we change this one to an oxidation, that would give us negative both of them. So we have to change this one to an oxidation. So there's your anode. Once you flip it, that becomes positive, add them together, and the standard potential for this cell would be positive 0.67 volts. Okay, so we're going to convert this one into a form where we can add them together. Right, so now we add them together, and we know that in this process, we transfer 2 moles of electrons. Okay. In fact, that brings up a point. This would not be, well, yeah, it is. 2 sulfurs, 6 oxygens, that's good. Okay, so that reaction's balanced. We have a standard potential, and we have a number of electrons, 2 moles. So now we can use the Nernst equation if we want to change the concentrations. N equals 2. Let's say that we're actually going to be at equilibrium. So that means the Q value is now K. We've rearranged this equation. See that? Since we got 0 on this side, it would have been 0 for the actual voltage, and then 0.0591 over N times the, let's see, the natural log, the log of K. So we want to find out what K is. So if we keep this one on that side, move this one over here, right? It flips it. We get N over 0.0591 equals log K. Now what we have to do is substitute. Wait a minute, I left out the E. Yeah, E. Right. Now what we have to do is substitute 2 in here and 0.67 in here. No, excuse me, wrong. I got it in the wrong place, don't I? Let's go back. Oh. As Fred Sanford would say, you big dummy. There we go. So now let's try that again. So now we have, this comes on this side. It becomes a negative, so both of them, positive would be equal to this one. 1 over N log K. Now this one on that side becomes N 0 over 0.0591 equals log K. Now, get back down here. There we go. Now we've got 2 times 0.67 here, divided by 0.0591. That's equal to log K, right? So this value together would be equal to 22.6 log K. So now K is equal to the anti-log of 22.6. There we go. 4 times 10 to the 22nd. So what does that tell us? That the equilibrium for this reaction is way to the right. There's a huge drive. You can tell that from the K. You can tell that from the voltage. We could calculate the delta G, and that would tell us it's spontaneous. The drive is to the right as written. And that's not unusual for redox reactions. There's a very strong drive to complete the reaction where electrons are concerned. Okay, what's the difference between E and E0? Well, E0 is under standard conditions. E can be any conditions. When is E equal to 0? At equilibrium, right? Dead battery. When is E0 equal to 0? Well, when both half reactions have the same standard voltage. And in this case, concentration cell. Most of the time, if you combine two different half reactions, they're going to be sufficiently different so that you get some voltage. But you're guaranteed an E0 standard condition voltage of 0 for a concentration cell. Okay, I'm going to pause for just a second and I'll be right back. Let's see, can I pause? Can I pause this recording? Pause the share? It's still recording. All right. Here's what I'm going to do. I'm going to come back to it so I can pause the recording. Okay, we're back. So now let me reshare this screen. And it's this one. There we go. Okay. So here's an example of a concentration cell, which was constructed with half reaction, nickel 2+. So, yeah, where's my rag? Sitting on it. So if we use the same half reaction where nickel 2+ is converted to nickel solid or nickel metal, then the anode side is going to be the oxidation. So we have, let's write this in line notation just for fun. So we would have the anode side would be the oxidation, nickel solid, to nickel 2+, right? That's aqueous. And then this side, we would convert nickel 2+, cathode side is reduction to nickel solid. And what I've done in this slide is identify which is which, nickel, cathode or anode. So this would be the anode side with the subscript A and A, and this would be cathode side with subscript C and C. Okay, so the only thing that will drive this reaction is a difference in concentration. And we're given that here in the description. Let's see, I got to get this out of my way so I can see what I'm doing. Here we go. Okay. So one side, the anode side is always the low concentration in a concentration cell, because we want to drive the reaction from here to here. And if we make this a low concentration, the tendency, according to Le Chatelier, is from here to here. So this is going to be 10 to the minus 4 molar concentration. And for simplicity's sake, we're just going to say that this is 1 molar. So the difference in concentrations between 1 molar and 10 to the minus 4th molar, which is a pretty big gap, right? 4 orders of magnitude difference. So we should get something. Actually, this is going to be more than millivolts. Well, it'll be millivolts, but it'll be measurable in terms of volts. Let's put it that way. So if this occurs at 25 degrees, and we know we can discover the E0, whatever the E0 happens to be. Oh, what is the standard potential for a concentration cell? Standard potential would have that 1 molar and this 1 molar. So E0 is 0. Right? That's a given. What we want, the actual potential. Okay. So if we set it up like that, and we just write the Nernst equation, oops, common log of Q. Okay. All right. So what we have to do is decide which is which. For a Q, we need to write the entire equation so that we know which one goes on top and which one goes on the bottom, right? So let's write this equation out in balanced form. So this is going to be the anode, which will be nickel anode, solid. And we're going to remove electrons from it. Anode plus 2 electrons, right? The cathode side is going to be the other way around. Nickel 2 plus cathode side plus 2 electrons yields nickel solid on the cathode side. So if we combine these two equations, then of course that goes away, and we end up with, let's see, maybe I can write it up here on top. We're going to have nickel anode solid plus nickel 2 plus cathode yields nickel 2 plus anode and nickel cathode solid. Okay, that's the balanced equation. So now we know that the Q is the anode concentration over the cathode concentration. Right? What happened to the solids? They don't count, right? Remember, when you write your K expression or your Q expression, solids drop out. They don't count. So we only have to include the solution concentrations of anode divided by cathode. So what does that tell you? In a concentration cell that runs spontaneously, the lower concentration goes on top, the higher concentration goes on the bottom. Okay, so if we plug in the numbers, which I'll have to erase in order to make room for, then this is equal to 0 minus 0.0591 divided by 2 moles of electrons, okay? And the natural common log of 1 times 10 to the minus 4 divided by 1. There we go. And if we resolve that, as I've done in the slide, then the electrical potential for this concentration cell is 0.118 volts. Right? So it's still kind of low. I mean, less than about 1/10 of a volt. So if we convert this to millivolts, what would it look like? Right? Because all voltmeters have a scale setting on them. Right? If you're going to measure very low voltages, you want to set it on millivolts. So this would be 118 millivolts. All right. Now, if you actually built this concentration cell in the lab, what voltage would you get? I would expect that to be the maximum. And the actual voltage would be less. But under what conditions could it be more? Well, I can think of one possibility. You didn't make up that solution quite right. Maybe you made up this one even lower concentration than that. And you made this one higher concentration than 1 molar. In that case, you would have calculated a larger value. So if you're calculating based on these values, but you made that error in mixing the solutions, then this would be higher. The other way around, if this were higher and maybe that one was lower when you prepared the solutions, then that value would be lower. But let's look at it from a practical standpoint. What are you likely to do when you prepare concentration cell? You're going to make a stock solution, probably 1 molar. And then you're going to dilute that to 10 to the minus 4th molar. So if you make a mistake with this one and you dilute it 10,000 times to get that one, what's the ratio? Ratio doesn't change because you made the same mistake on a percentage basis here as here, right? So if you do it that way, then you would not expect a higher voltage than you calculated. You would expect a lower always. Okay, just a practical demonstration of how things are usually done in the lab. All right, so we have this example of a galvanic cell, and we're saying that we've got a nickel electrode and a silver electrode, and you need solutions, of course. Well, you've got the solutions here. That's the aqueous nickel, aqueous silver. So you would need, in the nickel side, you would need a solid piece of nickel as your electrode, and this one you'd need a solid piece of silver. The question is, which one's the cathode and which one's the anode? Well, you need to look at the reaction. All right, let's go back. If you change the voltage, right, this is the standard reduction potential. So if you had the standard reduction potential of this one, right, and the standard reduction potential for that one is minus 0.23. And the standard reduction potential for silver is 0.80 volts. This one's minus. There we go. So this one is plus electron silver. All right, so which one's which? If we change this one negative, let's flip that one to make it the anode, then we're going to get a negative, and that means it's just the opposite. So we leave that one alone and change that one. Makes this positive, and then you add them together as this one. Now it becomes positive. Add them together, you get 1.03 volts. Positive. That's the way the cell operates spontaneously. With this one as the anode, where oxidation occurs, and this one as the cathode, where reduction occurs. Now we know which side to put them on. So the silver goes on this side, and the nickel goes on this side. So that's how you would sketch the cell, using a salt bridge in this case. And there's your voltage. That's your standard electrochemical potential for this cell. All right. Okay. So we've been making batteries. So let's look at some common batteries. The most common battery in the world is probably the lead acid battery. Every car's got one in it. Every industrial piece of equipment has at least one in it. Some of those are pretty huge. And they're made up of alternating plates of lead and lead 4 oxide. Okay. So notice how they're constructed. The lead 4 oxide is connected to the positive pole, and the lead is connected to the negative pole. So what does that mean? Well, the lead's connected to the negative pole because lead solid becomes lead 4 plus, and it loses electrons in the process, 4 of them. Okay? On the other side, the lead oxide, actually, that's not right. Actually, it becomes this. And I'll show you why in just a second. This is the anode that produces the electrons into the external circuit. Right? That's why the lead is here, and it emerges as the negative electrode there. Positive electrode says that lead 4 oxide, we add those 2 electrons to it, and now you get 2 plus. Okay? That's important. That for each of these half reactions, you get the same lead on this side. So what does that mean? That means that you don't need a salt bridge. You can immerse both of those plates in the same solution because their products are exactly the same, right? So when this one is reduced, it produces that ion in solution. And when this one is oxidized, it produces that ion in solution. Okay? So what's the counter ion, the counter anion for each of these? The sulfate. Right? And lead sulfate is insoluble. So I said that's in solution, but it's not. This is a solid. At this electrode, lead 2 sulfate is deposited on the plate. And at this one, lead 2 sulfate is deposited on the plate as a product of the reaction. Now the solution is this. Sulfuric acid, and it's very concentrated, right? So you don't want to spill any on you or your clothes. And in fact, before the advent of the sealed lead acid battery, there were ports, holes in the top, vent holes actually, and I'll have to explain that later. What the technician would do at the service station, before everything was self-serve, the technician would come out, if you requested, and bring this device called a hydrometer. A hydrometer measures the density of a liquid, and it's calibrated specifically for your battery acid. And he would suck up some of that solution into the hydrometer, and a dial would read whether it's discharged or fully charged or somewhere in between. And it's based upon the density of the solution. The higher the concentration of sulfuric acid in solution, the higher the density. So as the density increased, the charge increased. Okay. So that's the lead acid battery, and that's why you don't need a salt bridge in a lead acid battery, which makes them more compact, right? That's good. So what's the standard voltage for this reaction? It's in the neighborhood of 2 volts. It might be a little more. It's probably more than 2 volts. A little more. Let's just find out exactly what it is. Let's look up the reaction, if I can see that small. So for this reaction, the standard voltage, well, in the other direction, lead 2 plus to lead 2 plus to lead. Well, the one below it is 1.46, I think. No, that's not right. Yeah, maybe it is. That'd be easier to look it up in the textbook. Here it is. Okay. So the standard reduction potential for lead 2 plus to lead. Here it is. Lead 2 plus to lead is negative 0.13. So this reaction, the standard reduction potential is negative 0.13, but this reaction would be 0.13. Okay? This one is written as a reduction, so lead 4 oxide reduced to lead 2 plus. So it's lead 2 plus. Here it is, 1.46. 1.46. So if we add those together, we would expect that to be 1.59 volts. All right, so that's less than 2 volts. What seems to be the problem here? Here's the problem. That's the wrong reaction, because we have sulfate involved. With the sulfate involved, this reaction voltage becomes 3.5. So now 3.5 and 4.6 is 1, 7, 8, 1.81 volts. So maybe this one is written wrong also. Let me see. We need sulfate over here. What would that have to be? That would be 6.5, 1.65. Here it is, 1.69. So I got the wrong voltage in here. See how easy it is to make that mistake? So if you add those two together now, it's 2.04 volts. Okay, so that's the theoretical maximum for the lead acid battery. It's important that we include sulfur in that. The sulfate, excuse me. So you can expect to get 2 volts out of it. You might get less. Well, then the question is, we're expecting 2 volts out of each one of these cells. How do you get 12 volts out of a lead acid battery under the hood of your car? Well, it goes back to rules of circuits. I think Kirchhoff's laws. The total voltage in series, if you put these cells in series so that one's pushing into the next one, is pushing into the next one, so the plus to the negative to the plus to the negative to the plus to the negative to the plus, put them in series, then you add up each of the voltages. So how many cells would we need in series to give us 12 volts? You need 6. So that's why your battery, if you look at the top of your battery, even though it's sealed, it might have 6 plugs in the top of it, 1 for each cell, because the cells have to be separate, and well, no, they don't. Just put them in series. They do have to be separate. Yeah, the cells would have to be separate in order to put them in series. If they were in the same vat, then they would be parallel, and you get, your battery would last longer, but it wouldn't produce any more voltage. So if you put them in series, you get 12 volts out of that. 6 times 2 equals 12 volts. That's how you get a 12 volt battery. Okay, so I spent enough time on that. Let's look at a dry cell. This is just for illustration purposes. It's not something that you have to memorize. So this is called a dry cell simply because it doesn't have a spillable liquid in it. It doesn't have a spillable liquid, but it does have to be some form of solution. You've got to be able to allow the ions to move and for the reactants to come into contact with one another. So a dry cell is technically a misnomer. There's no such thing as a dry cell in this context. But we do make the reaction mixture into a paste. And the anode is the zinc liner inside. So there's your zinc liner, and there's the carbon rod that's simply there to conduct electricity. So the reaction itself occurs, well, at the rod for one reaction and at the zinc layer for the other. The zinc is the anode. So remember what we said. At the anode, you're getting oxidation, which means the zinc is being converted into zinc ions, right? So the mass of the anode, or the zinc casing, is decreasing over time. Theoretically, if you went far enough, it could start to leak because you'd start getting pits in it here, right? You're reducing the mass, you get pits, and then your paste starts to leak out. But fortunately, the anode is usually made thick enough so that the reaction reaches equilibrium before the anode is completely consumed. All right, here's another type of cell. It's another dry cell, Mercury Battery. And you've got the anode is, again, zinc. And the cathode is, this is a steel casing. So my guess is that that's carbon. And it's insulated. You need insulation. You got to keep the positive terminal away from the negative terminal or you get a short, right? And then you can't extract any energy from it. The Mercury battery is not used much anymore, simply because it requires mercury, right? There's mercury oxide. You know, that's probably not carbon. I bet that is a little bit of mercury metal right there. All right, so it's another type of battery. This is a fuel cell, which is another type of galvanic cell. It's a battery. The advantage to the fuel cell is, as long as you keep supplying hydrogen on the anode side and some form of oxygen on the, well, this is a hydrogen oxygen fuel cell. There are many types of fuel cells. But in this case, the hydrogen is on the anode side, oxygen's on the cathode side, and they are combined at high temperature. And when they are combined that way, we can access the electrons that are being used in the anode sent over to the cathode. So a fuel cell will produce a voltage in the external circuit, and as long as you keep supplying hydrogen and oxygen here on either side, the cell will continue to function. So it's not like a dry cell battery that eventually runs dead and you throw it away. A fuel cell will run indefinitely as long as you keep supplying reactants. So that's why the fuel cell is the holy grail of electric vehicles, because you can fuel it up as you would your gas tank, for our current gasoline engine cars. If you have a fuel cell, then all you need is a tank of hydrogen and a tank of oxygen. In this case, right? There are other types. Like I said, there are other types of fuel cells. You can keep supplying the fuel, and you can go as far as your fuel will allow you in an electric vehicle. So the distance of 250, 300 miles would be no problem, as long as you could refuel periodically with your hydrogen and oxygen. The problem with fuel cells is they operate at extremely high temperature, which from a consumer's viewpoint is hazardous. Right? They're very high temperature. Engineers have managed to reduce the temperature considerably over the years as they develop different types of fuel cells, but it's still an issue. And the other issue, of course, is a flammable gas. Okay, so that's the general scheme for a fuel cell. You can use something else in here to be oxidized and something else in here to be reduced. The concept is the same, whatever the oxidizing and reducing agents happen to be. Now let's talk about corrosion a little bit. Corrosion. A general definition of corrosion is a process by which a metal is returned to its oxidized state. So the metal becomes the anode in the corrosion process. And most metals, with very few exceptions, most metals in the Earth's crust are combined in some form of compound. In their ores, they may be combined with oxygen, sometimes they're combined with sulfur, sometimes with chlorides, or actually with oxides and hydroxides together. So there can be various combinations, but they never occur as the pure metal, with some exceptions, I said. One of those is gold, right? That's why when people go prospecting and mining for gold, it's a purely physical process. You just separate the gold from its overburden, and that's it. You got gold. That's why they call gold a noble metal. It doesn't react well with others. Now, gold does react, and we can find places in the earth where gold is combined with other elements. In that case, you smelt it like you would any other element. But the process of corrosion is the reverse. You're taking the pure metal and making it like its original ore. So it doesn't have the properties of the metal anymore, and that's bad. Particularly when you are building something out of a metal, you don't want it to convert to, say, its oxide while it's doing its job. That would not be good. For instance, a bridge. You build a bridge out of steel, which is predominantly iron, and when the iron rusts, it converts back to its oxide. So you have the iron metal plus oxygen, which would be a gas, and it produces iron oxide, which would be usually. It's actually more complicated than that, but I'm simplifying it for illustration purposes. So you want it to remain here, but it goes there. That's corrosion. In fact, this is a special kind of corrosion called rusting. Okay? It can happen to any metal, almost any metal. The noble metals, it's not too common. Noble metals are, let's see, there's gold. Another noble metal is platinum and palladium. Right? There's gold, platinum, palladium. Silver is rarely found in pure metal form. It can be. It may be an inclusion in a quartz crystal. That's common. But for industrial purposes, silver is usually in some form of ore that has to be smelted out. Okay, back to the topic. Corrosion, in this case, rusting. So this would be the conversion of this 0 oxidation state to this 3+ oxidation state. So iron to iron 3+ is the anodic reaction. We've oxidized it. Now, what do? Right, we can't let that happen. Right? And here's an illustration of what happens on the surface of the steel or iron. And in order to make that conversion, one water droplet sets up a galvanic cell. Right? Only the electrons are wasted. Okay. So we're not going to labor that point. The cathode reaction for this one is the conversion of oxygen in the presence of water to hydroxide. So we produce a basic solution in the process. And if you wanted to balance this equation, of course, you would balance it as an acidic equation and then convert it to a basic equation. But it could occur under acidic conditions. This is just in nature. That's what happens. In the lab, you can make it happen in acidic conditions. And if you drop acid onto steel, eventually it will accelerate the process. But that's another topic. So how do we prevent corrosion? One way is to exclude, and now we're talking about, in general, a corrosion involving oxygen. Right? So if the metal is exposed to the air, oxygen is very plentiful, right? 20%. So one thing you can do is coat the metal with something. We can coat it with paint to exclude oxygen. That works for a while until the paint weathers and flakes off. Or we could coat it with another metal, right? And anybody talk to your grandparents? It was common for households to have probably a half a dozen or more galvanized steel buckets. They were galvanized because they were dipped in molten zinc, which coated the metal with zinc and protected the steel underneath from rusting. Now, how did it do that? Well, galvanizing in itself coats the iron with a layer of zinc, right? So here's your air. Let's say we do it on both sides, right? So now air can't get to it at all. So this could be air, it could be water that's in your bucket, something in your bucket, whatever. That protects the iron from exposure to the oxidizing agent, which is oxygen. It also does something else. Zinc is more reactive with oxygen than iron is. So the zinc will form a zinc oxide coating on the outside. And after you get enough of that zinc oxide on the outside, it also protects the zinc underneath. So you don't want it to be shiny zinc on the outside. You want it eventually to be kind of dull and grayish, because that means you formed that protective layer of zinc oxide that protects the zinc, and the zinc protects the iron. If you rub off the zinc oxide or scratch it, then more of it forms to fill the gap. So, in order to protect the iron as the anode, the zinc becomes the cathode, and in the process, well, actually, the zinc is not the cathode anymore. This would be the anode if you were exposed to oxygen. But now we have another anode that is more reactive than the iron. And this is called a sacrificial anode. We sacrifice the zinc to save the iron. And this is common practice. You can put many ships that sail in salt water, and salt water is more corrosive because of the ionic strength of the salt water. We won't go into that right now. But many ships have a band of zinc around the hull below the waterline. And what happens is the zinc sacrifices itself to save the hull of the ship. Now, if the ship is sitting in the water and there's no power in the ship, then that zinc will eventually be depleted, because over time this zinc oxide will flake off. But what they do is, as long as there's power in the ship, they provide an external current. And what that does is it continuously reduces the zinc oxide to zinc, right? And protects the sacrificial zinc from corrosion as long as there's power in the ship. That makes the zinc band last longer. So the only time the zinc is actually sacrificed is when the ship has no power to deliver that extra electrons to reduce the zinc. Okay. What's another way to protect the metal? Well, you can form alloys, right? One alloy that was one of the first alloys was copper and tin. Now, that alloy was not developed in ancient times specifically for sacrificial anode or protection of the copper. It was devised to strengthen the copper for weapons. Right? But copper and zinc makes brass. And zinc, being more reactive metal than copper, protects the copper, and it does not corrode easily. Let's see if I'm correct in that assumption. Here we go. Let's use this one. So we look at the half reactions for zinc. You see, here's copper, 0.34 volts for copper to be reduced, and zinc is negative 0.76. So in order to go from zinc to zinc 2 plus would be 0.76 volts. And to go from copper to copper 2 plus would be 0.16. So this one is more likely to be oxidized than that one. It has a higher positive voltage. That's why zinc is more reactive than copper, and it protects the copper in brass. That's why you will see on boats, in particular, things are not made of steel. Generally speaking, they're made of brass. Brass is easier to work, and it doesn't corrode in the saltwater environment in particular. And it's cheaper to make than stainless steel and easier to work than stainless steel. Stainless steel is very hard. It's difficult to bend it, to work it at room temperature, whereas brass is easy to form, right? And it provides service without corrosion. So that's why ships will have things made of brass and not stainless steel. Now, sometimes they have to make them with stainless steel for other purposes, but whenever possible, make them out of brass. It's cheaper and easier to work. Those are alloys. Stainless steel, all right, I mentioned that one, but I didn't say what it was. Stainless steel is iron, carbon, right? You have to have carbon for stainless steel, so it's going to be less than 0.5% is a form of steel. And then you mix in chromium. Chromium, if we looked at the reduction potentials, we find that chromium is more easily corroded or converted to its oxide than is iron. So chromium sacrifices itself in the stainless steel to protect the iron. Now, originally, I can't remember who invented stainless steel, but originally, chromium was in the neighborhood of 35%, so it was very high. But here's what it does. In steel, you've got iron, chromium, so forth on the surface. Right? So, in contact with oxygen, chromium oxidizes first, right, and forms a layer of chromium oxide. So that would be, let's see, 2, 3, I think. Chromium oxide on the layer, on the surface. It reacts so fast that if you scratch stainless steel that's been polished and it's nice and shiny, you see the scratch? That scratch will fill with chromium oxide almost instantly and seal the underneath. So that's why when you polish stainless steel, it stays shiny forever. Because of that protective layer. Now, the other thing you can do with chromium, in fact, what they did first was the same thing as with zinc. You plated chromium out on the surface of the steel. It's a little trickier than that, though, than it is with just dipping your bucket in molten zinc. In order to plate chromium on steel, you have to use an electrolytic cell. You reverse the process. Instead of a battery, you drive the electrons backwards the other way. And we're going to look at one of those in a few minutes, I think. Let me get over here. And I'm already an hour over time. So, and we talked about cathodic protection already. By using a sacrificial anode. And the next slide, let's see, here we go. Second, let's make it here, there. So there's our sacrificial anode connected to the buried iron pipe. All we need is a way to get the electrons to the pipe and prevent it from corroding. So as the magnesium is consumed, it converts to magnesium plus ion and releases the electron into that circuit and then makes this the cathode. So that's cathodic protection by using a sacrificial anode. Okay. Now, electrolysis is the opposite of the spontaneous reaction forms a galvanic cell or a battery. We want to run that spontaneous reaction in reverse. We want to reverse it. So what do you need? Well, if the reaction normally goes this way with 1 volt, we need to insert an electromotive force of greater than 1 volt in the opposite direction. If we do that, then the reaction on the anode side will become the cathode. And the one on the cathode half cell will become the anode. It's just running the reaction in reverse. Now, what you can do is you can take what is now the cathode side, which was the anode, and run a charge in a circuit like that, and the anode now is irrelevant because you are providing the electrons from an alternate source. Right. So what happens at the cathode if you run the anode in reverse? Well, normally what you would see is electrons moving that way and metal ions going into solution. But if we run the electrons in reverse with sufficient voltage, then we get the metal moving back and deposited on the surface. Okay, so that's how you do an electrolytic plating. You take metal ions from the solution, plate them on the surface of the metal. It doesn't have to be the same metal. And that's how you plate. We used to have cars with chrome bumpers. Remember that? Chrome bumpers? They were made out of steel, but the surface was chrome plated so that they wouldn't rust. And they were shiny bright. It only took a thin layer of chromium to do the job. But in order to do that, you would have to provide a certain amount of certain number of moles of electrons in reverse to plate out a certain amount of metal on the surface. And that's where the calculations come in. All right. So in order to do the stoichiometry of electrolysis, you typically need to know what's the current. And we didn't mention that before, but I'm going to mention it now. Current is measured in amps, abbreviated A, and this stands for amperes. An ampere is a flow rate, and it's in terms of coulombs per second. How many coulombs are delivered to a certain point on the circuit each second? Okay. So coulombs is a charge, seconds is a time unit. But remember, coulombs is not easily converted into moles. Right? We need a conversion factor. So if you know the current that's being delivered and how long it's delivered, you can calculate a charge. So if you say amps or coulombs per second times time in seconds, then the seconds cancel and you have coulombs. So this would be the total coulombs or charge delivered to convert an ion of a metal into a metal on the surface of the electrode. But now we know that the conversion factor, which is the Faraday unit, right? So you need your conversion factor of, let's see, I don't even have it memorized. Here it is. 96,485. 1 Faraday is equal to 96,485 coulombs per mole of electrons. So now that you have coulombs, you divide that one into it, right? If you divide that by coulombs per mole, coulombs cancel, and you have moles of electrons. Right? So that gives you moles of electrons. Now you need the stoichiometry of the reaction. Right? How many moles of electrons are consumed in producing each mole of the metal? So that depends on charge. Right? If you've got, say, well, I don't know, chromium. Say you have a solution of chromium that has a 3+ chromium ions. Then you would need 3 electrons for each mole to produce chromium solid. Right? So there's your ratio, 3 to 1. So if you had 3,000 moles of electrons, you would get 1,000 moles of chromium. All right, so that's what this schematic is talking about. You need the current, you convert the current to the number of coulombs, convert the coulombs to the moles of electrons, use the stoichiometry of the reaction to find the moles of the metal. And then if you need to know the mass of the metal, you just use the molar mass of the metal to convert moles of metal to mass of metal. So, when you first, those of you who first started off with me in Gen Chem 1, I was hitting conversion factors pretty heavy. Dimensional analysis, we call it, because you use it over and over and over again in chemistry. So if you learned it once and forgot it, you better memorize it again, because conversion factors, dimensional analysis is where it's at. All right, so let's see. We can use, let's say we can use electrolysis to determine what metal it is that's in solution. How about that? Didn't think we could do that, did you? What do you need to know to determine the metal or any element, right? If there's your unknown metal, what do you need to know? Well, one of two things, right? You need to know the atomic number. If you know the atomic number, you got it right there. But suppose you can't do that, right? In this problem, you can't do that. The information is not there. So what's the alternate? Molar mass. And I've said it before, I'll say it again. As the atomic number increases from upper left to lower right, increases, the molar mass increases too. And in most cases, the molar mass is significantly different enough, one to the next, that you can use that to identify the element. There are only a couple of places in the periodic table where the molar mass is so close that it's difficult to tell the difference. For instance, let's see, argon. Argon is 39.948 grams per mole. Calcium is 40.08. Those are pretty close together. So if you found the molar mass and it was a decision between the two, how would you tell the difference? Well, if you're producing argon, it's going to be a gas. If you're producing calcium, it's going to be a metal. So there's an easy tiebreaker. So in the vast majority of cases, if you can find the molar mass of the element in this right here, molar mass of that element, you can identify the element. Okay, let's see if we can do it. We're looking for molar mass of our element. All right, what are we given? We're going to electrolyze the element, and it's nice of them. We're given a solution of the metal and the nitrate. All right, so what does that mean? This is -1 charge, so this has to be 3+. So you're given that. The metal ion is a 3+ charge. That's good to know. Because what? You're going to be doing this. That's what you're going to do, to plate that metal out. Okay? All right. So what else are we given? We're given the amperage equals 2.00 amps. Okay? And that current of 2 amps is delivered for 52.8 seconds. So time is 52.8 seconds. And the result is that we end up with 0.0719 grams of metal. Okay. So what do we need to know for molar mass? We need to know mass per mole, right? Mass in grams. So we've got to find both the mass, which we were given, and we need to know the moles of metal. How many moles is represented by that mass? We can calculate the molar mass, then we can find our metal. Okay, so how do we find the moles of that? Well, our key, our entry into this reaction is through the electrons, because this is a transfer of electrons. So this is coulombs per second times 52.8 seconds. Right? So that tells us how many coulombs of charge were transferred. 52.8. So that's 105.6. 105.6 coulombs. All right, now we need to convert that to moles of electrons. 105.6 coulombs. Coulombs per mole of electrons. So it's 96,485. All right. So if we divide that by, remember, is that correct? Unit conversion? We want to end up with moles of electrons. We start with coulombs, cancel the coulombs. Yeah, that's right. Divide by 96,485. So that is, let me Let me increase my number of significant figures here. Hold on just a second. Display. Fixed. 6. 1094. So it's 1.094 times 10 to the minus 3 moles of electrons. Okay? That's how many moles of electrons were transferred in this process. How many moles of metal does that represent? Well, for every mole of electrons, how many moles of metal? Well, for 1 mole of metal, we use 3 moles of electrons. So you divide 3 into that. That's 3.65 times 10 to the minus 4 moles of metal. Now we got mass, we got moles. So we just say mass is equal to, let's see, make some more room. Mass is 0.0719 grams per 3.65 times 10 to the minus 4 moles. Let's see what that is. 0.0719. 197. 97 grams per mole. Now we got a molar mass. We just take our chart and we look at it. We say, all right, that's 50. Let's keep moving down. There's 190, 92, 95, 96.967, 200. That's it. We're looking at M is equal to gold. All right. And that's how they make this costume jewelry. They just play out a very thin layer, a couple of atoms thick of gold on a cheap metal underneath, and that makes it shiny gold. And the more you wear it, the more you wear off the gold layer and eventually get down to the base metal, and then your jewelry looks ugly. That's why pure gold is better if you want to keep it for a long time. You know, like a wedding band. Now, this is 14 karat, which is what? What does carat mean? While we're here, if I've got 14 karat gold ring, what percentage of gold is that, right? Because it's an alloy, right? It's not pure. 24 karat is pure. So 14 divided by 24 times 100 is equal to 58.3% mass gold. Okay, so it's a little over half gold in that ring. They put other stuff in there. Lots of copper, particularly if you want it to be yellow gold. Put a lot of copper in it. Some silver. Silver's a lot cheaper than gold. I think the price of gold now is $1,800 an ounce. I haven't looked up silver. Silver's probably in the neighborhood of between $30 and $40 an ounce. That's a big difference. All right. So there's the calculation that I did on the board. Right. So you've got it there in case you made a mistake in making your notes. This is what happens when I'm not limited to time. If I can record my lectures, I'm already an hour over. Fortunately, when you get to the recording, You can skip stuff. Right? If you feel comfortable with something, you just skip over it, go to the next topic. Okay, in this case, let's see where we're at. This is pretty close to the end of the line. Almost there. All right, so let's say we have a solution of 0.1 molar in each of these ions. Lead 2 plus, copper 2 plus, tin 2 plus, nickel 2 plus, and zinc 2 plus. Predict the order in which the metals played out as the voltage is turned up from 0. So what does that mean? Well, let's take lead to begin with. So what's going to happen? Lead 2 plus 2 electrons yields lead metal. So at what voltage does that half reaction occur? All right. So we need to get our table. We use the book. So lead plus 2 electrons, that's a standard reduction potential. So we need lead plus 2 electrons. And here it is, 0.13, negative 0.13 volts. So that tells me that it's not spontaneous in that direction. It's spontaneous in this direction, because that's what you'd have to do to get a positive voltage. So when would the reaction go this direction? The reaction would go spontaneous to the right if you applied an external voltage in excess of 0.13 volts. Right? If you applied exactly 0.13 volts positive, then you'd get equilibrium. It's set at 0 volts, nothing would happen. So you need to exceed that by just a hair, and then lead starts plating out. So what are other options? Copper 2 plus. 2 electrons. So the standard potential for this one is copper 2 plus to copper metal. Here it is, 0.34. Plus. Is that right? Yeah. So in order to drive this reaction, actually this is spontaneous. So let's look. You can do that for each one of them. Look at their voltages and put them in order. And as you turn the voltage up from 0, the metals would form on the cathode, because the cathode is where reduction takes place, like that. So the cathode is the site of reductions. So you need a reduction potential to predict the order of plating. The more positive the standard reduction potential would be those first to plate out. I got the wrong voltage there, right? Did I get the wrong voltage? That's not right. That voltage should be 0.34. Okay, so I need to make a correction there. Okay, so the most positive one will be the first one to plate out, because it's the more spontaneous reaction. And the more negative it gets, the less spontaneous it is in this direction. Right? Negative means it wants to go the other direction, because if you flip it, then it becomes positive. So I need to make a correction there, but I think that won't affect the order. The next one is lead at negative 0.13, 0.14 for tin, nickel, and zinc. So I just need to change that value. That's not right based on our standard reduction potentials. It should be 0.34. All right. So what commercial electrolytic processes are used? Probably the greatest economic activity for electrolysis is in the production of aluminum. Aluminum, for the longest time, could only be produced by chemical means. So you'd have a chemical reaction, it would produce, the aluminum would precipitate out, and then eventually you'd collect enough to where you could make something out of it. But the process was so laborious and expensive that for the longest time, aluminum was more valuable than gold. That's why, to impress his guests, Louis XIV, King of England, instead of bringing out gold utensils for the banquet, would bring out aluminum utensils, which was a sign of his power and wealth. Eventually, a method was devised for electrolysis that separated aluminum from its oxide. The oxide of aluminum in its ore state is called bauxite. And there are places around the world where it's relatively concentrated, and it's just dig it out of the ground and do some preliminary purification and send it off to its destination for conversion to aluminum metal by the process of electrolysis. Now, that electrolysis was originally developed by Hall, who was a teenager who was interested in the process and did his preliminary research on the electrolysis of aluminum ores in his garage. Now it's much more refined and has been refined by other researchers, so that the process itself now is one of those hyphenated names. Okay, so you can also purify metals on a smaller scale. For instance, copper. Copper can be produced from its ore by physical means first to get the copper separated from it. And then you can use some chemical means to remove some of the slag. Eventually, if you want to use copper for conducting electricity, it needs to be very pure. So copper wires in your house have to be 99.999% pure copper. And the only way to do that is by electrolysis. The only economic way is by electrolysis. So you plate out the copper on the cathode, on the cathode. And then you can produce electrical circuits with it. Metal plating, right? If you want to make something look expensive when it's really cheap, you can plate gold or some other non-corroding metal on the surface. Or you can plate things with certain metals that will protect the underlying metal. We've talked about that. What I didn't say was when you plate chromium onto steel, you can't plate chromium directly onto steel, because the crystal structure of chromium as it forms on the surface of steel is radically different than the steel underneath. So they will not adhere to one another. So what you have to do is, when you have steel, you coat it with other metals, usually copper or maybe nickel. I can't remember which it is. But copper on one layer, nickel on another layer. Then you can coat it with chromium. So you need an intermediate metal because the crystal structure of steel and chromium are so radically different that it will not adhere. But you sort of bridge the gap with these other metals. Okay, metal plating. Now, the production of aluminum is a major industrial process. Another major industrial process, and I don't know the value, whether one is more valuable than the other, but the electrolysis of sodium chloride is how we get melt it, right? Remember, sodium chloride in crystal structure, you can't gain access to all the atoms. So you need to melt it. Then you electrolyze it, and you can produce sodium, metal, and chlorine gas. Chlorine is an extremely valuable industrial element, as is sodium. Right? So you can produce sodium hydroxide, which is used in numerous other processes. Chlorine gas is also used in numerous processes, not least of which is the production of bleach. And in that case, you redissolve the sodium in water, then you bubble chlorine gas through it, and you produce sodium hypochlorite, which is bleach. Sometimes they do it at the same factory. But that's how you get access to this metal and that non-metal, is by electrolysis. Okay. So this is a schematic of the Hall-Héroult process for producing aluminum. And you get the molten aluminum out the bottom. This process makes aluminum so cheap that now we can wrap our food in it, throw it away, or put our beverages in it, use them up, throw them away. That's how cheap aluminum is now. All you need is a source of aluminum ore, bauxite, and you want to add a little bit of sodium aluminum fluoride. And the reason you do that is because it lowers the melting point of the aluminum oxide, makes it more manageable. But the other thing you need is lots of electricity. Huge amounts of current are required. So that's why aluminum processing plants are set up in areas that have abundant energy. Either coal, right, in western Pennsylvania, where you have lots of coal, and you can set up a plant where you can burn coal, make electricity, send it to the aluminum processing plant, and you're good to go. Or there were aluminum processing plants in the Tennessee Valley. The government paid for that electricity by building dams on the Tennessee River, producing cheap hydroelectric power, which is common in some places, right? Northwest U.S. in Washington State, Oregon State, you have lots of cheap electricity there from hydroelectric. But you need that lots of electricity, lots of current to run the process. So that's where you look for sources of cheap energy. Okay, let's see. You can electroplate your spoon in silver, right? This is an example. Here we're producing sodium and chlorine in this process. So the engineering is important here because you want the anode is the source of the chlorine gas, because that's the pause. No, pause. Hello? Yes. Yeah, I don't think I can get her out of bed that early. Okay, appreciate it. Bye. Sorry for that interruption. When the doctor calls, everything stops. Okay, so at the cathode, we're taking sodium ions and making sodium metal, right? That's the side of reduction. And the liquid sodium is drawn off there from that cathode. And the cathode is probably carbon. That's cheap enough to use and reuse and deplete and replace easily. The anode is where we take chlorine, Cl minus, remove an electron, and get chlorine gas. So that's the site of oxidation. And it's set up so that as the chlorine bubbles out of the molten sodium chloride, you can capture it easily here. So that's why the construction is this way. Oh, we're done. All right, took me long enough. So that's chapter 18. So what you'll want to do now is get your review document and dig into those problems and do your homework, right, on the Cengage website, and finish up your labs, because there's still some people that are way behind with their labs. And some who have turned in a lot of labs I haven't graded yet. I apologize, but I will get to them. Fear not. Okay, so that's it. I'll stop the share. And we're done for today. And we'll stop the recording.